Alright, so this is a beam bending problem. This is a review for your exam. This is a cross section. It says the outer diameter is 160 millimeters and the inner diameter is 140 millimeters. And this is a beam, so it's a circular beam. And they give you the lengths. Obviously, we're going to have to draw a free body diagram where you're going to have to get the reactions at, this is point C, this is A, and this is B. So we're going to have to get the reactions at C and B. Then we're going to have to draw the bending moment diagrams, the shear diagrams. Then we're going to have to calculate. So I combined this problem with chapter 6. So you're going to have to find Vmax, Mmax, find the maximum bending moment, and find the maximum transverse shear. So this is like one problem, but it's two chapters in one. So you could expect something like this maybe on the exam. Okay, so let's start. Let's draw a free body diagram of this beam, and let's get the reactions at C and B. Okay, so this is a free body diagram. 4 meters, 1 meter. Okay, so how are we going to find the reactions FC and FB? Sum the moments, right? If we sum the moments at C, we could get FB, and then summing the forces in the y direction, you could get FB. Okay, so let's sum the moments at C. Taking counterclockwise to be positive. You have, remember, this is a distributed load, so you need the integral form. You could break this up. You could break this up into a single point load and put it right in the middle, but then your bending moment diagram is going to be wrong, so you need integration. Okay? Not to find the reaction, but when you draw the bending and shear diagrams, you're going to have to use integration. Okay? So this moment, this distributed load is going to cause a moment, right? So that's minus, it's going to go clockwise, so it's minus the integral. It starts from 0. I'm labeling my coordinate axis from here. So it's 0 to 4. And the distributed load, W sub x, is 3 kilonewtons per meter. So it's just x times 3. So remember, the integral equation is x wx dx. This is for a moment, okay? W of x is 3, and just x is x, okay? So it's minus the integral from 0 to 4, x times 3 dx, plus 4 times fb, plus, this is also going counterclockwise, so it's plus 1 multiplied by 2 is equal to 0, okay? We got everything. All right, so you just evaluate this integral. You guys know how to integrate 3x, right? It's 3x squared over 2, evaluated, this is minus, evaluated from 0 to 4. Then you have plus 4 fb plus 2 is equal to 0. Okay, you could solve for fb. You know what this is. It's just 3 times 4 squared over 2. The 0 drops out when you subtract that. So you can solve for FB. So FB is equal to, you guys know how to evaluate an integral, right? I hope so.
Why do we use an integral for this?
Why do you need to integrate?
Yeah.
I told you before, if it's a distributed load, right? Okay, so this function, W of x, is equal to 3, right? Kilonewton per meter, right? Let's say you had some curve, right? You're going to have to integrate. You could break for this one. You know it's a rectangular distributed load. You could multiply it by the distance 3 times 4 and then put the load right in the middle. You could do that, but then your bending moment diagram is not going to be correct. Okay? All right. So you need to integrate. Okay. Alright, so FB is equal to 5.5 kilonewtons. And you could check this if you want. You could multiply this 3 kilonewtons per meter times 4, and then the point load is right in the middle, so it's 2, from FC, it's 2 meters in, right? And you could sum the moments, you'll get FB is still 5.5 kilonewtons, okay, which we would expect. Alright, so now let's get FC, right? So how are we going to get FC? We'll sum the forces in the y direction. Summing the forces in the y direction to be 0, taking upwards to be positive. You have FC plus FB minus 2 minus what? Okay, but in integral form. Yeah, it's 3 times 4. Yeah, it's going downwards. What is it as an integral? It's an integral. If you start your coordinate axis from here, what is it?
1 to 5.
1 to 5, exactly, that's right. And what's W of x? We said it's just dx. Have you guys seen this? You never saw this? Alright, so you can move this to the other side. We just solved for FB, then we can solve for FC. So FC is equal to 2 plus 3x evaluated from 1 to 5 minus FB is 5.5. So FC is equal to 8.5 kilonewtons. Okay. All right. So now that we got the reactions, that's good. Now we're after finding the maximum shear in this beam and the maximum bending moment. Okay. So we're gonna have to draw 2 free body diagrams. We're gonna have to cut it over here, somewhere between A and C, and then we're gonna have to cut it over here, somewhere between C and B. All right, so let's cut it between C and A and C. Okay. So this is a free body diagram from this is your x-axis, this is your y-axis. So it's from 0 is less than x is less than 1. And this is meters, okay? You don't have to write this out like this, it doesn't matter. Okay, so this is a free body diagram right over here. You have the 2 kilonewton force, you have a shear force V, and you have a bending moment M. And this distance over here is x, right? Because it's anywhere from 1 to, it's from 0 to 1, okay? So this distance is x. Right? So we want to know what the shear force is, V, and we want to know the bending moment, M, in this cut section over here. So let's just sum the forces in the y direction to get V. You're only doing this to finding, you want to find the shear and bending moment diagrams. So you have to know the shear everywhere in the beam, the bending moment everywhere in the beam. Okay? So minus 2 minus V is equal to 0, so you have V is equal to -2, and it's kilonewtons, right? So you have the shear force, now you have to find the bending moment. If we sum the moment at point A, this is point A over here, taking counterclockwise to be positive, you have Vx, that's going clockwise, so it's minus Vx. Plus M is equal to 0, so M is equal to Vx. So M is equal to minus 2x. Okay, you guys got that? All right, so this is a moment. So what does the moment tell you about this section? Is it linear, quadratic? Linear. It's linear, yeah. So it's a straight line going downwards like that. Okay, so that's the moment between this section, A and C. All right. Let me erase this. Alright, and so now we're going to have to cut it between C and B. Can I erase this?
No. Just give me like 30 more seconds. I'm good. Thank you.
Alright. Okay, so now let's draw the free body diagram between C and B. So you have 1 is less than x is less than 5, okay? So we're drawing this section right here, somewhere in between C and B. Meters, okay? So let's draw the free body diagram of that. So I'm cutting it somewhere between C and B, okay? This was FC, and FC, remind me, was 8.5 kilonewtons, right? And we have this distributed load over here. This is why you need integration, because if you don't use integration, you're not going to get the right bending moment diagram. You'll see in a second. Okay? And this distance over here is x. This distance is x. It's from A to somewhere where we cut it between C and B. And this distance we know is 1. You guys are fine on this free body diagram analysis? Alright, so we're going to have to, we cut it over here, so what forces do we expect? Shear in a moment, yeah, so B and M. Okay, so now we have the complete free body diagram. So let's sum the forces in the y direction to get B again, and then let's sum the moments at A to get M, okay? So, summing the forces in the y direction to be 0, taking upwards to be positive, you have minus 2 plus 8.5 minus the integral from 1 to x, 3 dx, right? And then you have minus b is equal to 0. Okay. All right, so we can solve for v. Move v over to the right, so you have v is equal to minus 2 plus 8.5 minus 3x evaluated from 1 to x. Okay, you can substitute that in. So v is equal to minus 2. So that's minus plus 6.5, right? Yeah. Plus 6.5 minus 3 multiplied by x minus 1. Okay? That's good. And so now v is equal to minus 3 times minus 3 is a plus 3. Plus 6.5 is 9.5. So you have minus 3x plus 9.5. Okay? Alright, so that's your shear at this section. And that's also linear. Alright, so now let's get the bending moment at this section. So let's get M. Alright, so let's sum the moments at A. Let me write it, it's going to be long. Summing the moments at A to be 0, taking counterclockwise to be positive. You have 1 multiplied by 8.5, that's positive because it's going counterclockwise. Then you have, this is going to make it go clockwise, this distributed load. So you have minus the integral from 1 to x, x times 3 dx, right? And then you have minus bx plus m is equal to 0. Okay, we got everything? 1, 2, 3, and then the multiple. Okay, good. All right, we got everything. Okay, so we want to solve for m. We're always after this bending moment m over here. So you can move everything to the other side, solve for m. So you have m is equal to bx plus 3x squared over 2 from 1 to x minus 8.5. Okay, so I just moved all this to the other side, right? And we solve for Vx. What's Vx? Sorry, we solve for V, not Vx. We solve for V. V's over here, so you can stick this in over here for V, and then you can just get a moment equation just in terms of x, okay? So let me give you the final result. You guys know how to evaluate this integral. This term over here is just 3 over 2 times x squared minus 1 squared, okay? That's this term over here. Right? So, and we can substitute for v. V is equal to minus 3x plus 9.5. Okay? Alright, so you're gonna get a bending moment. Is this linear or quadratic? It's quadratic, right? And if you broke this up into a single point load, you're not gonna get that. You're gonna get a linear moment. That's not right. Okay? So you can't just say this is 3 times 4, it's 12. And then it's located, what, 3 meters in? You can't say that. I mean, you could technically do that, but it's going to mess up your bending moment diagram. So you're going to get it wrong on the test, and you don't want to get it wrong. Okay. You guys got it? Oh, let me give you the moment. Okay, so, alright, so let me give you the moment. M is equal to minus 1.5 x squared, after you simplify everything, plus 9.5 x minus 10. Okay, so this is equal to this. Alright, so we know it's quadratic, right? So now that we got the shear and bending moment at every section we need to, we can draw the shear diagrams and the bending moment diagrams. Okay, so what I'm going to do to make life simpler, I'm going to just list what we just solved before. So you can see everything when we draw the bending and shear moment diagrams. Okay, so for this section we found V is equal to minus 3x plus 9.5, right? And this information is from from 1 to 1 is less than x is less than 5 meters. Okay, so that's for this section. And then for the first section, we found that V, well, let me list it manually. Okay. We found that M is equal to minus 2x and V is equal to minus 2. And this is from 0 is less than x is less than 1 meters. Okay. All right, so we have these two sections, right? So now we can draw the shear diagram and the bending moment diagram. Okay, so let's draw the shear diagram first. Okay, the shear diagram looks like this. Okay, so you have 1, 2, 3, 4, 5. All right, so what are we going to label? This is in kilonewtons, by the way. This is kilonewtons. This is in meters. X is in meters. So what are we going to label the y-axis? Well, look at these equations, right? So from 1 is less than x is less than 5, we're going to have different shears at like these points, right? So what do you guys think? Well, we know from 0 to 1, we have a constant shear force, right, of -2. So obviously -2 should be on here. So it's -2, right? Label that -2. And it's constant from 0 to 1. So you have a flat line, right? But what happens at 1 from this shear? When x equals 1 over here, you have -3 plus 9.5, right? That's 6.5. So you're going to also have 6.5. This is positive, so it's 6.5, right? So it starts here and then it shoots straight up to 6.5. And then what happens? Huh? It goes down, yeah. It goes down until when you plug in 5, what happens? What value do you get? You get -5.5, right? Okay, so it goes from here, 6.5, and then all the way at the end of the beam, it goes down to here, right? And where is the shear force 0? That's important. The shear force is 0 tells you what? Where the maximum bending moment is, right? So you need to know that. Okay, so when is the shear force 0? You just set this equal to 0. You solve for x, so you know where the shear force is 0. Right? So 0 is equal to -3x plus 9.5. X is equal to, move this over, you get 3.167. Okay? So x is over here. V is 0 over here. This is 3.167. Okay? So the shear force is 0 over here. So you get a line like this. Okay? Right? And what happens after 5? The shear force is 0, right? So it goes back up to 0. Right? Because there's nothing going on after this beam ends. So there's going to be no shear force. So this is what the shear diagram looks like. Okay? So that's your shear diagram, right? That's like, that could be like 10 points on your exam or something, I think. So this is important to draw it right. Okay, so from this, what were we after? We're gonna have to find the maximum transverse shear. So what do we want from this diagram? We obviously want the maximum shear force, right? So what is it? You have -5.5, -2, and then you have 6.5. So this is obviously the maximum shear force. So V max is equal to 6.5 kilonewtons. Very important, because we're going to have to find the transverse shear, which is BQ over IT, right? And this B is the 6.5. So, because we're going to ask for the maximum transverse shear. All right, so now we want to draw the bending moment diagram. So let's just, I can erase this for now. We don't need it anymore. Okay. This is X, this is M, and M is kilonewton times a meter. Guys, if you want to talk, can you talk outside because it's distracting to me. I'm trying to help you guys out. Alright, so this is 1, 2, 3, whoop. 4, and let's make it longer. 5. Okay, so now we have to figure out our y-axis for M. So what moments are we going to have on the y-axis, right? At x equals 0, what are we going to have using this? At x equals 0, we're going to have the moment is 0, right? Obviously in the beginning and at the end of the beam, the moment should be 0, right? You guys agree? So obviously 0's on there, so we have 0. And at x equals 1, we have -2 again, right? So -2. And then what are we going to have for this section over here? Well, first of all, we know M for this section, we know it's minus 2x. So we have a straight line that goes like this until we get to 2, right? This is a straight line. And then we have a parabola. We have an upside down parabola. So we have a shape like this, right? And there's a maximum point over here. We have to find the maximum point because we remember the moment at the end at 5 we know is 0, okay? So we know this point. What you could do if you want to waste time on your exam, you could plug in 1, 2, 3, 4, 5. Or you could just know it's a parabola, draw this shape, and just say, okay, well all I need to find is the maximum point, right? So the maximum point, and notice something else. This is a parabola, right? If you want to find the maximum point of a parabola, what could you do?
Negative b over 2a.
No. You have this equation m of x. If you want to find the maximum, what do you want to do? It's use calculus. You take the derivative and set it equal to 0. Exactly. Take the derivative of this, set it equal to 0. Well, what do you know? You take the derivative of this, you're just going to get b, right? Okay, that's why I said you could just set b equal to 0 and solve for x. So if you take the derivative of this, you get minus 3x plus 9.5. You solve for x, you get this. So when you plug this into m for x, you get the maximum moment, right? And the maximum moment you get when you plug in 3.167, m is equal to 5.04. Okay, many people are going to be tempted to just say, okay, well, let's plug in 1, 2, 3, 4, 5. Oh, I plugged in 3, I got 5. That's the maximum. It's not. It's 5.04. Because I'll be honest with you, when I did this, I was like, okay, let me plug in these values. And I was like, oh, 5's the maximum. And then I checked in the back of the book. I'm like, oh, it's 5.04. What did I do wrong? And I'm like, let me take the derivative of this, set it equal to 0, solve, and then plug it back in. I'm like, oh, it's 5.04. I would have lost points on the exam. So, yeah, it's stupid not to get this. It's pretty easy. So,
if we had said we rounded though, would we been okay?
I don't know. Yeah, but yeah, in this case, you know, 5 and 0.04. It's not a big difference, but maybe another problem there's going to be a little bit of a difference. So, all right. So we know the max is 5.04. So you have a parabola that looks like this. This is the maximum point at 3.167. That's when the shear force is 0. So we expect the maximum bending moment over there. So it looks like this. I know my picture is going to be pretty whack, but it looks like that. This is the maximum over here. Okay, this is 5.04 kilonewton times a meter. Okay? Alright, so this is your bending moment over here. This is your bending moment diagram. Right? So we found M max is equal to 5.04 kilonewton times a meter. Right? So we got B max and M max. Great. Well, now we want to find the bending stress. Okay, they want to know what's the maximum bending stress in the beam. Well, we know sigma max is equal to M, well, the moment's max, it has to be max, My over I, right? This is a cross section over here. This is the neutral axis. It's right in the middle. Okay, so what's Y? This is R, I'll call this R sub 0 for the outer radius. The inner radius is Ri, right? So the outer radius is just 160 divided by 2, so that's 80 millimeters. And Ri is equal to 140 divided by 2, so that's 70 millimeters, right? So you have the inner and outer radius, okay? So what is Y? If we want to find the maximum bending stress, just give me in terms of variables. What is it? I just labeled them. Is it R naught or Ri? Well, R sub 0. Huh?
R naught.
Yeah, R naught. Yeah. So M over I. Okay, so we're going to have to calculate the total moment of inertia. So this cross section is hollow in the middles, right? So it's solid over here, and it's hollow in the middle. This is like a really good exam problem. So that's why I picked it for you guys. Okay, I'm going to erase this now. Okay, so what's I? I is equal to what?
What is the diagram?
If you assume the vertical shear is upward, then we will get
You're gonna get the reverse. Yeah, you're gonna get the reverse. That's okay. That's fine. That's fine. Yeah, that's definitely fine. The book conventionally just puts a shear force all the way down, so that's why the diagram looks like that. But if you put it up, everything would be flipped. Okay, and that's perfectly fine. You're perfectly right. Okay. So what's I? What's the moment of inertia?
pi over 4 times r naught.
Pi over 4 times
R naught minus Ri.
Yeah, that's right. Remember, it's to the fourth. Okay. So this is a total moment of inertia, right? It's just the outer minus the inner. So I is equal to pi over 4 times 80 to the fourth minus 70 to the fourth. Okay. So I is equal to. Let me give you that value. So it's equal to 1.331 times 10 to the 7 millimeters to the fourth, which is equal to 1.331 times 10 to the negative fifth meters to the fourth. Okay? Alright, so we got the total moment of inertia, we got the maximum bending moment, and we have the maximum distance where we're going to have the maximum normal bending, we're going to have the maximum normal stress or bending moment stress over here or over here, right? Over here it's going to be in compression, here it's going to be in tension, okay? So, sorry, this is in tension, this is in compression. So, what do we got? So you got M max is equal to 5.04 times 10 to the third. This is Newton times a meter, multiplied by R naught, which is 0.08 meters, all over the total moment of inertia, which is 1.331 times 10 to the negative fifth meters to the fourth. Sorry for speaking. Okay, so the maximum bending stress we get is 30.3 MPa. So that's the first part of the question, and the second part of the question, which I added in there, is find the maximum transverse shear. Okay?
Is that a -5? I'm saying you just literally just erased it.
Oh yeah, this is a minus 10 to the negative fifth.
I think
Yeah. Any questions for this first part? This is definitely going to be on the exam. Huh? No, but I'm positive they test this every year. So I mean, if I was a professor, I would put this one problem to test 2 chapters. Then it's less degree, you know. You cover 2 full chapters in one problem. And I know Cook did something similar. His problem, I gave you his problem last exam, but he also asked for the transverse shear. I think it's a summer session, so they're ahead of you guys. So they do it really quick. So we want to find the maximum transverse shear. So that's equal to V max Q. Remember, it's a total Q, so I'll just call that QT. Actually, let me just leave it as Q, whatever. So Q over IT. All right, so let me ask you guys something. Where does the maximum transverse shear occur? Neutral axis, right. So this is NA, the neutral axis. And we have to find the Q in this section. This is the inner radius, this is the outer radius. Okay? Alright, so we want to find Q of that section. Well, we know it's hollow in the inside, so we know this is equal to this, right? This is a neutral axis. So I'm just going to draw a little pictorial diagram over here. You have, if you calculate this Q, subtracted by this Q, this radius is R0, this radius is Ri. Well, that's equal, this is a neutral axis, by the way. Neutral axis. Well, this is just equal to that, right? Okay, so that's the pictorial diagram. So if you find Q of this, subtracted Q of this, so I'll call this 1, 2, and it's equal to this, okay? So we want to find the total Q, so Q is equal to Q1 minus Q2, right? Because we're subtracting out. Is everyone fine with that? The most important thing to understand is the maximum transverse shear occurs at the neutral axis. Because if you don't know this, you don't know where the hell to start on the next part. So you need to know that. So it occurs at the neutral axis always. Okay, so Q is equal to A1 times Y bar 1 minus A2 times Y bar 2. And if he doesn't give you this on the exam, like if he gave you a shape like this, you know that Y bar for a semicircle, he'll give it to you. He definitely will. I don't think he'll make you memorize it. It's 4R over 3 pi, right? I just know it because Gupta just put this on his exam for statics. So this is Y bar for a semicircle. So let's use that. So Q is equal to, well, A1 is equal to pi times the outer radius, right? This is R0. So it's pi R0 squared, right? That's the area multiplied by Y bar. So that's 4R0 over 3 pi. So now you guys see why I turned this diameter into a radius, right? Because everything, you could put this in terms of diameter, but I know everything in terms of radius. So that's why I changed it to a radius. Okay, and this is minus, losing all the chalk, pi Ri squared, right? That's the area of this semicircle. And what did I forget? This is a semicircle, so this is over 2, right? This is over 2. Why didn't anyone correct me? Okay, so, and this is being multiplied by 4 Ri over 3 pi, right? Okay, so you know the pi's cancel, the 2 and the 4, you get 2 on top. So you get Q is equal to, I just noticed I made a mistake. I wrote pi R0 squared. And I just caught myself because I have to use my calculator now. Alright, so if someone could calculate this for me, it'd be great, because I made a mistake in my notes. Alright, so I said it was pi R0 squared, but that's the area of the whole circle. You have to divide it by 2. So you get, this reduces to what? 2/3 times R0 to the third minus Ri to the third, right? Okay, so that's what you get when it reduces. So you have to calculate Q. What's Q? I calculated wrong in my notes. I gotta fix that. This is 80, this is 70.
So it's 112. So it's 112,667.
So this is 1. What is it like in scientific notation? 1 point.
Oh, 4.1.
1.26.
1.26.
1.126, sorry. 1.126 times 10 to the 5th. You need to put 1 there.
Yeah, there you go. Times 10 to the what?
10 to the 5th.
Fifth?
Yeah.
Okay, millimeters to the third?
Yeah.
Alright, so that's, what is that in meters?
So it's times 10 to the negative 12. Will be 1.126 times 10 to the negative 7.
Okay. Okay. Alright, I'm trusting. You
Sorry,
just,
wait, that's 9.
you have to divide it by 1,000 cubed.
Sorry, negative 4. Yeah.
Okay. Alright. Okay, so this is Q, right? So Q is equal to this value over here, right? So we know Q, we know V max, we got that from the shear diagram. We got I, and what's T in this case?
10 millimeters.
Careful, who said 10?
Idiot.
No, he's not stupid, but look.
Is it 5?
There's 2 T's, right? So it's this diameter minus this diameter, or in terms of the radius. Yeah, look, this is T, this is getting sheared off, and this is getting sheared off. So T is equal to 20, yeah, 20 millimeters, that's right. Okay, you're right. So T is equal to 2 times R0 minus Ri, right? So this is equal to 80, this is equal to 70. So T is equal to 20 millimeters. That's perfect. Okay? So we got everything. So we know this, we know this, we know this. So plug it all in. So you have tau max. So someone's going to have to calculate this because I calculated Q wrong too. So this is equal to 6.5 times 10 to the third newtons, multiplied by Q, which is 1.126 times 10 to the negative fourth. Meters cubed, all over the total moment of inertia, which I erased, which is 1.331 times 10 to the negative fifth meters to the fourth, multiplied by 0.02 meters. Okay. What does that turn out to be? That's your answer. Whatever it turns out to be. Someone just plug and chug so we can calculate. 2.8? 2.6 or 2.8? 2.8. Oh, 2.8. Times 10 to the 6. So it's 2.8 MPa. Okay. Alright. So that's a maximum transverse shear. So that's chapters 5 and 6. And I'm going to be out of time, but I'm going to try to do this as quick as I could. Do you guys want me to try to do this problem really quick or no? Yeah, sure. Alright, so this is from Cookman's exam.
Yeah. Send it? Wait, what?
Okay, alright, so you have this 2D stress, and I want you to find the principal stress and the principal angle. Okay? You could use Mohrs circle, but on your exam, I'm just going to do it how you want on your exam. I did it with Mohrs circle, but I'll teach you Mohrs circle one. All you need to know is the principal stress, sigma 1, 2, is equal to the average, sigma x plus sigma y over 2, plus or minus the square root. This is tau max. Remember, on your exam, tau max is just whatever's in the square root. It's sigma x minus sigma y over 2 squared plus tau xy squared. Okay. This is a maximum shear. shear stress, this square root thing, whatever it turns out to be, and this is sigma average. Okay, so he's going to ask you what's the maximum shear, just this. Okay, I think it's stupid because this is just memorizing equations or whatever. All right, it's better to know Mohrs circle. All right, so okay, so what's sigma x? This is sigma x. Is it minus or plus? It's in compression, right? So sigma x is minus 50 MPa. What's sigma y? Plus 20 MPa. And we need to know what's tau xy. Well, look at this. This is a positive phase. Tau xy on this surface is pointing downwards, right? So we know tau xy is minus. Do you guys understand that? That's something you guys aren't going to understand. You're just going to memorize. You're going to be like, okay, I have tau xy like this. This has to be minus. If it goes up, it's positive. Most people just, I'll be honest, when I first took this course, I was like, I don't know why it's minus, but let me just memorize it. Okay? But it makes sense. This is a positive surface, and tau is going downwards, so it's minus. Right? If it was this is a positive surface. If it's going upwards, it's positive. Likewise, on this surface, this is a negative surface, right? This is a negative surface, and it's going to the right. So a negative plus a minus is a minus, so it's a negative. So this is minus 60 MPa. So that's the real reason, right? And if we had tau xy to the left over here, well, it's a negative surface in the negative x direction. A negative and a negative is a positive. So that's something you guys won't learn in this class, but I'm giving you my knowledge. Okay? So tau xy is negative 60 MPa. So we got everything. You just plug and chug. You put this number here, divide by 2, this number over here, this number here, here. You get the point. So sigma 1, comma 2 is equal to it's equal to 54.5 MPa, comma, negative 84.5 MPa. Okay, so that's your solution, and then he's going to ask for the maximum. Shear stress. So he's going to ask for this answer over here. So you just plug in whatever. You plug in these values over here, and you get tau max is equal to this. So tau max is equal to it's equal to 69.5 MPa, and then they ask for the maximum. They ask for the principal angle. So you have to memorize this equation. When you guys do Mohrs circle, it'll make more sense what these are. Okay, just for right now, you have to memorize it. Okay, so so tangent to theta p is equal to 2 tau xy over sigma x minus sigma y. So you want to solve for 2 theta p. You take the inverse, so arc tangent of 2 tau xy over sigma x minus sigma y. Just stick the values in, so you get theta p, and then you divide by 2 at the end. You get theta p is equal to 29.87 degrees. Okay. Good luck on your exam.
Wait, there's 2 of them, right?
Huh?
You have to also add.
Yeah, you could find another one, but that's good. You find one, it's fun.
Cool.
Yeah.